Well, thank you all for joining this talk. We're going to talk about how to facilitate transactions in SystemVerilog and VHDL. And as Mark said, my name is Rich Edelman, mentor of Siemens Business. I'm in the California office, so I appreciate, and let's just say an easy schedule. It could have been much more difficult. So what are we going to talk about today? We're going to talk about transactions, a lot of them. So this is a picture of a system. It's an AES encryption system. There's 4 AES engines. And at the top, we see the UVM sequences. So those are transactions that were generated by the UVM. In the next thing down, we see some transactions generated from Verilog memory. And then there's some registers, they were instrumented. And then the actual AES engines, their gate level design, and so the interfaces are instrumented, and you can see the engines there. And then finally, we have some VHDL memory that is a part of the system. They were instrumented also. So, and what you can see in this diagram is that the virtual sequences up here, they start some transactions, and then the colors mean that those are the IDs, and so those go through the system, and you can sort of see the colors going through the system until they finally, the results land in the VHDL memory. So there's many ways to get transactions, and you can basically just instrument your code. So whatever code you have VHDL code, you have Verilog code, you can just instrument it. You can use the UVM. So if you instrument your code, you write some code and you insert instrumentation. If you use the UVM, well, it just sort of comes for free, not quite for free, but almost, and you get transactions. And that can be VHDL or Verilog. And then if you have a monitor that you're using already to monitor something, well, a monitor usually, in my world anyways, is looking for things that happen, like a transaction, something happens, maybe it has a start and an end and some attributes. So you have your monitor, your existing monitor, and you instrument it. So that's an easy way to get transactions. And then another way is to do something a little more sophisticated. Maybe you create a recorder that is, well, it's just exactly like a monitor, except it has one job. It's just to record transactions. And then you either build it as part of the UVM, maybe as the publisher subscriber, or maybe you just do something real simple. You just bind it in. So you have your existing code and you bind in a recorder. We'll talk about all those things today. So here is instrumenting some code. So this is just a Verilog always block, and I've put in some instrumentation. So whatever this code is doing, it's setting up some memory and then initializing something on the AES side, and then collecting some attributes and ending the transaction. So here's the begin and adding attributes, and then this is the result. So this is what comes back from the AES encryption, and then we end the transaction. So by sprinkling in these seven lines, I'm going to get transactions showing up in the wave window. And in this case, there's some, we'll talk about the arguments, but we have a stream and it has a name. And then we have a transaction handle that was created by beginning the transaction. And then what are we putting in it? Here's the value, some memory we're putting in, some address, some block, and we give them names, string names. So how about that API that I'm using? So there's a Verilog version and a VHDL version, they're equivalent. So we can add attributes, so that's values of things, name, value pairs. We can have a transaction be a certain color. Maybe we have an error checker, and in our code, we've determined there's an error. We can just make that transaction red if we want to. We can add a relation like parent, child, predecessor, successor. You saw a begin transaction, give the transaction a name. There's some optional parameters with time and parent. Creating a transaction stream, you give a stream name and a kind, delete, end, and free. So this API has been around for a while, and this happens to be the mentor API. The other guys, they all have the similar API. So it's relatively easy to use API. So what happens if you decide to use the UVM? I said it comes for free, so it's almost for free. It does record things automatically, but you have to do a little work. You have to define a function called doRecord. And then we recommend you use the UVM record field macros to define attributes. And then when you're just using the UVM in normal mode, start item, finish item, you'll get your things recorded. So here's a sequence that we have, and we've implemented doRecord. So this is the doRecord function, and it's going to call super.doRecord to see if there's anything in the base class. And then it's going to record the attributes that it wants. So it wants to have a name, a start address, and an end address in this particular transaction. So what's going to get recorded? Those three attributes. Okay, so here we see that doRecord, and it's got its name, its address, and its end address, so start and end. And so when it refers to that variable, it's just simple. It just goes and uses scoping, and it gets the value from that class. So these are the attributes that it's going to record. Get name, name is going to get returned by the function getName. That's a UVM call. So it's going to return the name of this thing. And then in the wave window, we'll get those attribute field names, and then we'll get the values in the actual wave window. So that's a sequence. That's a UVM sequence. So that comes for free once you do record. And the same thing for a UVM transaction. So we define a doRecord, and it has some different attributes, and it's exactly the same. It's going to get recorded. And then we'll be able to see the sequence here and the transactions that sequence has started right there in the wave window. Here's a blow up of that. So we have our sequence with some attributes, and there's a transaction below. Must have been a read transaction went out. So what is happening in the UVM? So here's my sequence code, and I'm going to call start item, finish item with a randomize in between. And so in start item, way down in the UVM, it does a begin transaction. And then finish item, it does way down in the UVM, it does an add attribute and an end transaction. So that's what's happening in the UVM. You get these built-in calls. So what if you wanted to have a monitor with transaction recording? So you have this monitor and you're going to instrument it. So here we have our run phase. So it's a monitor with a run phase. And in the very start, we're going to create a stream. And then this monitor really is just a forever loop. So that stream got created, and now the monitor is doing its monitoring job, and we've added these highlighted lines. The monitor is doing its monitoring job. It's waiting for ready valid, and it's going to do whatever it does to take things off the interface and fill up a class. Eventually, this monitor is going to do an ap.write, and it's going to send that transaction out to other subscribers. But we just wanted to instrument the monitor and put in our transaction. So here is the transaction. It's a simple little interface, and it has a read. And so when the read happens, we call begin transaction with the name read, and we record the attributes that we want to record. And then if it's a write, we do the same thing. This line's not highlighted. Begin transaction write, and then we record the attributes and end the transaction. So it's really simple. I don't know, what's that, 10 lines of code to add. So in that example, we took a class-based monitor and we instrumented it. And so that was our monitor that got instrumented. But we could also do a thing where we create as I was talking about earlier, we could create a recorder which has just one job. It's not a monitor, it's a recorder. And the monitor could publish information over to the recorder, and then the recorder just does one job and it records. So what about other things we can do with the recorder besides publisher subscriber? Well, we can use bind. So we could have a recorder and we just bind it right in. We don't have to change any code. We have this external implementation that gets bound in. So for bind, we have, perhaps I shouldn't have called it monitor here. I should have called it recorder. We have a recorder that's going to get bound in. It does the same thing. It's a module this time instead of a class. and we're going to create a stream. But before we get there, what's going to happen is we have this existing test bench top, and we have a block and a DUT, and we're going to bind the recorder, right into the DUT. So essentially, it looks like it's an instance in the DUT. No edits to the file though. So we've started the monitor, we have the stream created, and then it's a similar little piece of code. It's waiting for ready valid. It's a monitor. It's in an always block this time instead of a forever loop like we saw previously. And we're doing our begin transaction, add attribute, add attribute, add attribute. So you see this piece of code, the only thing it does is actually build that transaction. So it's bound into that instance, and it's monitoring the signals that are there that it got connected to. So it's connected to signals in our hardware. So it's recording some attributes, ending transactions. It's doing everything we need to do to get transactions. So we could actually bind this very deep into our DUT instance hierarchy and monitor those transactions. So what about the VHDL side? So the VHDL API is used really just the same way. We're instrumenting a bunch of VHDL code here. This is an example from our release. And it's just calling create transaction stream, and then add attribute, begin transaction, and so forth. And you end up with a pretty picture. This does it has some hierarchical relationships between the transactions. So we just take our code and we instrument it. What about things like the UVVM? Where should we instrument that? So for that one, I'm not a UVVM expert, but for that one, I took one of the examples, the BitViz IRQ C-test, and I poked around to see what it was doing, and it has a bunch of calls, check and write. So it's doing some work to do some verification on the little example. And so I decided that I would instrument check and write. And so first I have to create those streams. I decided I was going to have two streams, one for write and one for check. And then I found the write code and I instrumented it. So I said, well, when write starts, this maybe was an easy one to instrument because there's wrappers around what the workers. So the SBI write is doing the real work. There's a wrapper called write. So I just put the instrumentation in there, begin, add a couple attributes, and end. And then same thing for check. It's a wrapper. So I did a begin, add attributes, and an end. And I just want to show the picture. So we end up with two streams, a write stream and a check stream. And so all of the write transactions are coming out on the write stream. And of course, the check transactions are coming out on the check stream. So we talked about streams, and I didn't really explain them. And we talked about transactions. So there are some choices to make about transaction modeling. You need to decide how you're going to model them, how you're going to see them when they get recorded, and then also there's some decisions about what attributes you actually want to record, and well, of course, how you're going to do the recording. Are you going to use the UVM, Verilog, VHDL? So there are decisions to make, but it's pretty easy once you make those decisions. So for basic transaction modeling, well, what is a transaction? It has a name, and then it has name value pairs that are attributes. So there can be as many of those as you like. What else does a transaction have? It has a begin time and an end time. And then we like to say that it lives on a stream, or it runs on a stream, or it is owned by a stream. I don't know. There's lots of ways you can talk about streams. They're a convenience, really, for how we're going to display them in the wave window. So what about stream modeling? Well, we can just create one single stream. And so one stream is very easy. You say, create the stream, and then you put transactions on it. You say begin transaction on that stream. So for a system, you might have, read address and read data. write address, write data, and acknowledge. You might have that all on one stream. It just looks very nice. So the pros, it's very easy to think about. It's very easy to do, and you just see all your transactions on the same stream. And then, of course, the cons is all the transactions are on the same stream, and it can get quite busy. What about multiple streams? Well, you might decide that you want to have multiple streams where you're going to have a read stream maybe and a write stream. And so the read and the write are separate, and of course you're going to put them. You're going to call the begin transaction with the stream. So there'll be a read stream and a write stream. So that's nice to look at. Instead of 2, well, you could do 5 streams. So that could be each of the channels, for instance, could be on their own stream. What happens when transactions overlap? So we're drawing these things in the wave window, and it's nice to see them spread out. So this is a picture of transactions that overlap. We might have these. We would like to show them in an interesting way. But the thing that we don't want to have to model in our recording code, we do not want to have to model the overlap, because you can't predict what the overlap is going to be until the system is running. You might have a certain limit to how many transactions can be in flight. It might be a dynamic control. So what the system does is it will create substreams. And so the substreams are created automatically. Essentially, when there's an overlap, a substream will get created, and the overlapping transaction will get put on the substream. So that then it'll draw very nicely, and you won't have to know ahead of time how many parallel transactions you have. So this is a case where we have 3 kinds of streams. The first stream there with the number 1 is in order. So these are transactions that are in order. It's a very regular thing, and it's being displayed on a single stream. The second stream here is an overlapping stream, and it has 4 substreams. And those were created automatically just from the way that the traffic came through on the different transactions. So the fact that there were overlapping transactions was detected by the system, and they got recorded in a nice way. So you can see that they're overlapping and things are happening in parallel. And then for out of order transactions, this one happens to have 6 substreams. And now out of order means that the answers are coming back not in the order that the question went out. So the write address and then the data may come back in a different order to other transactions that were issued. So this system responds. It's the same test bench actually running, and it's just a different way of starting the transactions, whether they're overlapping or in order. And so the system is responding and recording in a useful way. Okay, so we went quickly through that, but I hope you can see that transactions are very easy, and they can really go anywhere. They can go in the UVM or Verilog, SystemVerilog, UVVM, VHDL, System C as well. I didn't mention that, but System C also. So transactions are very easy, really, to add to your code, and there's very little code to add. But the great thing about transactions, if you ask me, is they provide a different kind of view of what's going on in the system, and a very easy for your eye to find patterns, easy to think about things and reason about things at a higher level. I'd be glad to take questions now, or you can contact me by email there, Rich Edelman at mentor.com.
Thanks very much, Rich. There's already 1 or 2 questions, guys. Just put your questions into the chat window. Tudor is already commenting that, as you can see, the implementation of the transaction recording, I guess, at the internal stuff for the internal digital interfaces. It would be nice if the designers did this. Do you have any comments on that? Because I also, when I have brought transaction recording to designers, they've been amazed because they're used to dealing at signals and not having the information presented to them in such a clean way, right? When you look at the waves and it tells you this is exactly what's going on at this point.
Yes.
But do you have any comments on that?
So I think the question is, how do we get more people to use transactions?
Designers in particular, I think.
Oh, designers are, those guys are really hard. They're stuck in their old ways, so it's really hard to get them to do things. But just like you said, if you show them these pictures, they get it immediately. And then my experience has been that they, since the API is really small and it's really easy to understand, they'll take that away and they won't tell anybody, and they put it into their code. So they put it into their monitors or into their IP, bind it in, and then all of a sudden I'll get emails saying, hey, what about this? What about that? And they'll have a picture in it with the coloring, because they like to color the thing. They like to color the transactions themselves because that means the color, they assign meaning to the colors. So it has worked, but they're very tough to convince. But the best way is with pictures.
Yeah, I tend to agree. I know you didn't mention it here, but one comment before we go on to another question there, because we still have a reasonable amount of time.
Yeah.
I find it very useful to provide a callback to the register model so that we can actually provide the name of the register when we see some internal bus.
Yep.
You didn't mention it here because your focus is different. What other things like that do you find are valuable? Or, yeah.
Boy. Yeah. So, I mean, if you're instrumenting, if you're recognizing a transaction and then you record it, that's one thing, and you can get a nice, pretty picture. But you're right, you can do callbacks to alert other parts of your system. Maybe I think that's what you're getting at.
Actually, it was more to provide the name of in this case, simply providing the name of the register.
Oh, I see.
Yeah,
I see.
saying, hey, I've got an address. Is there a register of this? Yeah, this is its name. And
Yes.
you tag it on as an attribute.
Oh, I see. So that would be an attribute that you would add by going and looking it up in the recorder. Yes, that's a really good idea. Let's see, other things that we put in as attributes. Sometimes there's related information that you can go fetch. I can't think of any off the top of my head right now, but I know that some people put look up things in their recorder to go find other related information.
Okay. You can see there's a very good question from Aurelian. I hope I'm pronouncing that correctly. Is there a proposal to standardize the transaction API, because we all fall over this? The subtle differences between the vendors.
Yeah. So I've seen people. So I haven't looked at the other guys' APIs in a while. I think they're very similar. Maybe the arguments are switched or something. The standard that I always go by, I think it was even a Cadence guy, and he put a standard out. I don't know, 10 years ago, and I don't think it ever.
Standard, you mean? I guess.
What's that?
A de facto standard.
Yes.
Not an actual standard.
Mm-hmm. Yes. Right. And maybe it was even more than 10 years ago. And he put out there's a paper, you can go find it. I think it might be in my paper in the references. And that's what we based our API on. And I was surprised that it didn't get adopted by the other vendors. But everybody has such a thing, and it would be nice if it was standard. I agree.
Another good question from Ole here is regarding the simulation performance hit.
Yeah,
it's not zero, but any comments on it from your side?
Oh, I'd like to say it was 0, but no, it's not 0. So when the simulator's running and you have events happening and you're recording transactions, I mean, if you have a big chip, if you have a decent size circuit, transaction recording is not the problem. That's very small. I mean, you could think of these things as just integers that are getting recorded or strings, and they're only, they're not, you don't want to record transactions on every clock edge. That would be a problem, but if you do anything on a clock edge, it's going to be a problem. So we haven't seen transactions be the problem anywhere.
And that's
But
coming from the
it's not
guys
zero.
that complained about the field UTL macros.
Yeah.
Anyway, that's a different topic.
Yeah.
One observation from my side, at some point I did notice that if we did a blanket turn on of a transaction recording, I think it was the base sequences or sequencers or something were all recording something in the background, and it was measurable, 10%.
Yeah. Okay.
And
Yeah,
we
there's
said,
something
that's pointless. So we turned them off and only turned on our monitors by default and high-level sequences explicitly or something like that. Any comment?
There's some. You're right. There is something that is deep in the UVM that you can turn on, and I haven't looked at that in a while. We don't use it. The way that we like to think about it is just sequences, start item, finish item. And then if you have your own monitors or drivers or something, I mean, you have to instrument those yourself. It would be nice if there was some standard there, maybe for UVM things, instead of just having everybody instrument their drivers and monitors, because a lot of times that's where the real fun is. But yeah, the UVM recording stuff is a little, it could use some, let's say, some housekeeping.